Okay, just very quickly, I reconciled my 182, negative 182, and it really is negative 180 as it had to be. And I had to actually work through all this and work through this part wrong, work through this part, which I did right, and it's much simpler. If I just plug the 19 meters in here, 10 newtons times 18 meters is 180 newton meters. Square of 19 meters is 361. You multiply it by 1 newton per meter, it ends up in newton meters. And then the subtracting what we get for the 1 meter, I get 10 newton meters minus 1 newton meter. Then I work this out, and it worked out right, just as I expected it would. At 1 meter you get 8 newtons, at 19 meters you get negative 28. 8 newtons, negative 28 newtons, averages out to negative 10 newtons. Multiply that by the 18 meter displacement, you get negative 180 newton meters. But this ends up negative 190. Well, I didn't see it right away. I had the 180 from averaging these. It got into my head, so I, instead of multiplying my 10 newtons times the 19 meters that I should have, I multiplied it by the 18 meters and got 180. This should really be 190. So now it's this, and it does end up 180. So I got turned around on the numbers, but the numbers are straightforward. Now the bigger part of this is, what did we do? We considered what happens when you apply a net force to a mass through a displacement, and we find out if we multiply the net force by the displacement, what we get is always equal to the change in the quantity 1/2 mv squared. That's the work kinetic energy theorem. And you're probably aware that 1/2 mv squared represents change in kinetic energy. We then applied that to this situation, and we determined that to get this thing started, in order to reach the ground, since you can't have negative kinetic energy, you have to give it at least 180 newton meters of kinetic energy. If you started from rest, it goes this way. If you started from rest, it doesn't get down here, because at rest it has 0 kinetic energy, and between here and here it has to lose 180 newton meters of kinetic energy, and it can't end up with negative kinetic energy, because 1/2 mv squared is never negative. So it's a very profound idea. The idea that the work, the F net delta x, is equal to the change in kinetic energy. Let's write that down. Okay. Also, in terms of this example, it's not necessarily F net delta x, because you don't always have a uniform net force on a constant mass. It's the integral of F net dx that's equal to the change in kinetic energy, and this is just a special case for when F net happens to be constant.